That was a really impressive talk on bouquet, Brian. It's going to be difficult for me to follow, and I swear I didn't steal your spectrogram visualization. That's a little bit embarrassing. It's like I showed up to the party wearing the same dress. Okay, this is something I've always wanted to do. Everybody in the room whistle at the same time. Okay. All right, it was beautiful. So my name is Luke Campagnola. I'm a neuroscience researcher at UNC Chapel Hill. In the kinds of experiments that I do, the experiments are very short, and we need to collect as much data as we can in a very small amount of time. And so in order to make sure that goes well, we need to be able to see all of that data as it's coming in so that we can make sure everything's going all right and react to it appropriately. So several years ago, when I was ramping up my dissertation work, my advisor and I decided to start building a new data acquisition system in Python. And so that meant we were in the market for a library that could do fast data visualization. And unfortunately, the obvious choice, matplotlib, was not really fast enough. And after some hunting around, we finally settled on using Qt's graphics view, which is a really nice high-level 2D visualization system. And that worked pretty well for a while, and everything was okay. And then fast forward a few years later, we started being a little bit unsatisfied with graphics view, especially because we knew that there was a lot more that we could do if we could get more of the power out of the GPU. And at the time, Qt wasn't really using the GPU so much. And at the same time, sorry, I have to take away the pretty visualization. So at the same time, a few other projects appeared on the scene. So one of these was Gallery by Cyril Razant, and Cyril showed us that it was possible to do millions or tens of millions of points in a plot and update this in real time. VisPy was another by Elmar Klein, who's now working with bokeh. Glumpy is by Nicolas Rougier. And Nicolas showed us that it was possible, it's tricky, but possible to do a lot of the really nice 2D rendering that you expect from a 2D graphics library in OpenGL. And previously, I had mostly ignored OpenGL because it's a very low-level system. And it would have taken me far too long to reproduce in OpenGL what Qt's graphics view was already giving me. But given that there seemed to be a lot of shared interest in doing this, and everyone was kind of going in the same direction at the same time, after a flurry of emails, VisPy was born, and we also sort of decided to work on this project together with the idea that it would supersede all of the other projects. And in the case of PyQt it would supersede Qt graphics view as the underlying visualization platform. So what is VisPy? VisPy is a pure Python library, and I have an asterisk next to that I'll get to in a minute. So the question is, how are we able to achieve very high performance in a library that's pure Python? And I hope you've already guessed the answer is that VisPy uses OpenGL to offload as much work as possible onto the GPU. And the way we're able to do this is by inserting GLSL, which is the OpenGL shading language, into our Python. And we hand that off to the OpenGL subsystem, and it compiles it and runs that code on the GPU. And this is awesome for us because it means that we get compiled code basically for free. There are no extra installation dependencies in order to make this run. And all modern OpenGL implementations have these compilers on board. So the benefit to us is that it makes VisPy much easier to distribute and to develop. And the benefit to the user is it makes it a lot easier to install. So what can you do with this extra power now that you've got it? You can either visualize more data than you were visualizing before, or you can do the same amount of data with faster updates, a faster refresh rate, Or for the same old refresh rate, you can get lower CPU load. And for me, that's particularly important because I'm doing data acquisition systems that need fast access to the CPU. So I want to give you a quick overview of the kind of problem that we're dealing with the GPU. The way it works is you start out on the left side here with your raw data. This is your data on disk or streaming in from a camera or wherever you've got your data. And ideally, there may be a little bit of preprocessing, but ideally this data is going to be streamed directly to the graphics processor without any changes. And then OpenGL on the graphics processor does work in two stages. The first stage is called the vertex shader, and the second is a fragment shader. And in the first stage, what happens is your raw data is passed through a series of coordinate system transformations until each point in your data has assigned to it a specific point on screen or off screen. And so what you end up with is a series of basic primitives. These are either lines, points, or triangles. It's very primitive. But these are all assigned their locations on screen. And then the GPU rasterizes this, which means it takes the area of the primitive and decides which pixels are inside that area. And it sends that list of pixels out to the fragment shader. And the job of the fragment shader is to loop over every one of those pixels and decide what color goes inside. And between these two things, we're able to do pretty much all of the drawing that we need to be able to do. And the really nice part about this is that we can insert any code into the vertex shader and the fragment shader that we want. It makes it very easy to customize and optimize the graphics that we're doing. I want to give you a quick example of this. Is my demo still running? So this right here is just an example of an image displayed 4 times, but with different coordinate system transformations applied to it. And these transformations are computed on the GPU. The CPU doesn't touch this at all. So you can combine together transformations, stack them together arbitrarily to make more useful transformations. And it's really easy to customize this. If you can write down the forward and inverse transformation function in GLSL and the same in Python, you can use that transformation with any of the visuals that we have. So VisPy is divided up into 4 layers in its architecture. At the bottom, we've got the very low-level stuff that gives you the most flexibility and control over OpenGL. And at the highest levels, you have a very simple API that gets your data to visualization as quick as possible. VisPy.glue is our object-oriented wrapper around OpenGL. OpenGL itself is rather verbose and a bit awkward and clumsy to use. So VisPy.glue wraps this up in a nice object-oriented Pythonic interface. It also has another important function, which is to take all of the OpenGL commands that are headed out to the GPU and put them through a queue first. And that queue can be serialized and then, for example, sent to a browser to be displayed in a WebGL context in IPython notebook, or it can be streamed onto disk and replayed later, or streamed across the network, etc. The next layer up is VisPy.visuals, and this is basically the core of VisPy. These are all of the objects that you can draw with VisPy without going back down to OpenGL and making your own. And these include things like points, lines, triangles, the stuff that OpenGL provides, but also more complex things like text images, volumetric rendering, and also visuals that require some amount of analysis on the data. So, for example, spectrograms, histograms, isosurfaces, contour plots, things like that. VisPy.scene then sort of ties together all of these visuals and brings them together. It's a scene graph, which means that all of the visuals are given a hierarchical relationship to each other, and you just define a few of those transformations. And what VisPy.scene gives you is a much more automated way of managing all these visuals. It gives you interactive view boxes and cameras and lighting, and it also takes care of handling mouse input. And then finally, the highest layer right now is VisPy.plot, which is similar in concept to MATLAB, Matplotlib, that sort of a thing. So for the rest of the talk, I think I'm mostly going to stop yakking and show you demos. these first two demos are just examples of the kinds of things that you can do with VisPy.plot right now. This is just a basic, simple plot, the sort of thing you might expect, but it took us an awful lot of work just to get to this point. The simplest things, for some reason, tend to be difficult in OpenGL. This is another simple example. This is 500,000 points in a scatter plot with accompanying histograms. And here we have some volumetric rendering. And the images to accompany it. These are all from the same data set. Okay, so those are just examples of the sorts of things you can do right now with VisPy.plot. And I should stress that this is very, very early in development. And the demos that I've just showed you won't run if you go and check it out right now. But we're getting there. What's next? It's like Christmas, right? Okay, so this demo basically just demonstrates that we can do picking and mouse interaction. Standard quiver plot, and this one got me thinking, maybe we can use the GPU to do something more interesting in terms of visualizing vector fields. And that's how I ended up with this little demo, which is more than just pretty. I think there are actually a lot of good uses for this kind of a visualization. In particular, you may have seen things like this online for showing wind flow patterns. This is great. So way back in the beginning when I started writing PyQt-graph, I was completely tickled that in pure Python, without writing any C code, I could make a plot of 10,000 samples and have it update and pan and zoom in real time. What you're looking at here is 10,000 plots of 2,000 samples each. Okay, this is all. So this data is being generated on the fly. It's streaming to the GPU in real time. And so when we talk about the kinds of big data that we want to be able to visualize, this is roughly the order of magnitude that my laptop can handle right now. So that's sort of the limit we're up against. And I threw in a little nonlinear transform just for fun. All right, so all of this is being, really, we generate the data, we send it to the GPU, and it does everything for us. So this here is a force-directed graph. It's nice if you happen to be into that sort of thing. What's next? Oh, the one you've all been waiting for. So this is really a proof of concept. It just shows that we can, in fact, serialize those OpenGL commands and send them to a WebGL context in IPython notebook. It's interactive. It's fast. This is a molecular model of a Me cell, if I'm not mistaken. Very few of the examples in VisPy right now run in IPython, but that's something that we're working on. And this is my last demo. And this is the only point I'm trying to make with this is that although we are writing VisPy specifically targeting scientific visualization, I think we imagined that it's a pretty general purpose graphics library, and there's an awful lot that it could be used for in the future. So you can look up VisPy online. You can pip install VisPy, but as I said, don't expect to be able to do the things I've just showed you today, except maybe for a few more weeks. And there's going to be a sprint at the end for VisPy and PyQt-graph both. So if you're interested, drop by and have a chat with us. Say again. I'm sorry, I can't hear you.
In the example, I didn't see any text being rendered. I remember a while back looking into OpenGL and kind of got the text rendering atrocious. I don't know if it has gotten better.
In OpenGL in particular?
OpenGL, but also like through VisPy.
So VisPy does have text rendering. You might have seen some text on the axes of some of those plots. It does have text. It uses a scaled vector field method for rendering the text. But yeah, I mean, OpenGL doesn't provide anything for you in terms of that. Really, you have to write your own fragment shaders to draw the text. Oh yes, pure Python. So all you need is NumPy and any of the variety of supported backends. So it runs basically everywhere. We haven't tried running it on any mobile systems yet, but I presume that's not going to be terribly difficult.
A comment and a question. The comment is there seems to be some synergies between VisPy and VisPy potentially. What are your thoughts on that?
So the question was, there seems to be some synergy between Bokeh and VisPy, and that has been discussed in the past. And in fact, Almar Klein, who was instrumental in bringing VisPy about, is now working on Bokeh. The word from Almar Klein is that it might not be possible or useful to go down that road. Like he says things are a little bit too different between the two systems to really consider that useful. Maybe that will change in the future. We don't know.
My actual question was actually OpenGL is undergoing a lot of changes right now because CPU and GPU are moving closer and closer together. AMD, for example, wants to have shared unified memory space, so OpenGL will change according to that.
Mm-hmm.
That's a 1.0 version or updated version not available. Which version of OpenGL are you supporting?
Okay, so the question is, given that OpenGL is in a lot of flux right now, which version are we supporting? Right now we're targeting OpenGL 2.1, which is pretty old, but it also means that it's supported almost everywhere. And it's just new enough that we actually have these programmable pipelines. As time goes on, we can see about adding more and more recent features. Are we okay?
So I only managed to look really briefly at but it seems like there's a lot of writing of shader code in various things, like for example, the Campagnola. Is like what we saw today. Is there a lot of shader code involved in writing that? Do you expect there to always be a lot of shader code?
So the question is, do you have to write shader code? Or more generally, do you need to know anything at all about OpenGL? The answer is, if you're working in the first two layers, if you're working on glue, or if you're writing your own visuals, then yes, you need OpenGL and shaders. If you're working in the top two layers, no. You don't need to know anything about OpenGL or even the underlying graphics hardware in order to use those.
I think we'll defer more questions to the break, and thank Luke again for an excellent talk.
Thanks very much.